Good day and welcome back for part 4 of our discussion on L'Hopital's rule. Let me begin by just reminding you of how L'Hopital's rule works. If we have a limit of the form f over g, and it is an indeterminate form of type infinity over infinity or 0 over 0. And recall what that means. An indeterminate form of type 0 over 0 means the limit individually of the function in the top and the bottom both approach 0. If it's type infinity over infinity, that means the limit in the top and the bottom both approach either plus infinity or minus infinity. In either case of these indeterminate forms, L'Hopital's rule tells us that the limit can be written in an equivalent way as the derivative of the top divided by the derivative of the bottom. And before moving on to discuss some new indeterminate forms, let me give you some quick reminders of our previous work. If we wanted to evaluate the limit as x approaches 0 of sine x over x, we can think of this very intuitively. As x approaches 0, the function in the top all by itself, sine x, goes to sine of 0, which is 0, and the x in the bottom goes to 0. This is an ideal scenario for L'Hopital's rule. Limit as x approaches 0, take the derivative in the top, divide it by the derivative in the bottom. Cosine is a continuous function everywhere, and remember with a continuous function, you simply take that value and substitute it in, and cosine of 0 is 1. And note, this should be a reassuring answer because the limit as x approaches 0 of sine x over x is something that we investigated and a limit we used quite a bit back in Calculus 1. In terms of the limit as x approaches minus infinity of x e to the x, to help see what each term is doing individually, remember it's always nice to have a graphical perspective. The graph of e to the x is the standard increasing exponential function. So as x approaches minus infinity, we're thinking way to the left, that function is going to be approaching 0. And as x approaches minus infinity, x by itself approaches minus infinity. So this is one of those secondary types of indeterminate forms, 0 times infinity. How we can handle this is to rewrite it algebraically so it becomes one of these more familiar indeterminate forms of type infinity over infinity or 0 over 0. And our algebraic technique is to just form a fraction. And I think the easiest possible thing that we can do in this case is just rewrite as x over e to the minus x. You certainly could rewrite as e to the x over 1 over x, but I think that's going to be maybe a bit more involved than writing it in this simpler form. Now as x approaches minus infinity, the x in the top is going to minus infinity, and let's think again graphically. If you were to graph the function e to the minus x, it's the reflection of e to the x over that horizontal axis. And as we approach minus infinity, so when we put in those very large but negative inputs, the function itself is approaching infinity. So we're in this scenario where we can apply L'Hopital's rule. L'Hopital's rule tells us we need to take the limit where we differentiate in the top and we differentiate in the bottom. Now I'm going to rewrite this algebraically just to make my final observation as easy as possible. This is minus e to the positive x. And as x approaches minus infinity, we see e to the x in blue is approaching 0. So 2 examples to get us going, reminding us of how we use L'Hopital's rule in our previous discussions. It turns out, though, that L'Hopital's rule can actually be applied to even more scenarios. we can apply L'Hopital's rule when we have so-called indeterminate powers. So indeterminate powers are when you have a limit of a function f of x raised to a function g of x. And there are certain scenarios where this ends up being an indeterminate form in the sense that it has no associated meaning that we can take from it. And those scenarios are as follows. When you have 0 to the 0, that would be f goes to 0 and g goes to 0. Another indeterminate power would be when you have it of the form infinity to the 0. There's no associated meaning with these, along with 1 to the infinity. And it turns out that in all three of these cases, we can algebraically rewrite f raised to the g of x and reduce it down to one of our previous indeterminate forms and apply L'Hopital's rule. And that algebraic simplification should not be a surprise. It's exactly how we would rewrite this if we were going to differentiate it. We would say it's e to the natural log of f of x to the g of x. Remember, an exponential and a natural log undo each other. But specifically in this case, that troublesome exponent function comes out front of the natural log. So we would have e to the g of x natural log f of x. So to handle these indeterminate powers, we will rewrite using properties of exponentials and natural logs and then evaluate the limit. Let's go ahead and explore a few examples. So let's go ahead and see if we can apply this algebraic technique we've discussed to evaluate the limit as x approaches 0 from the right of x to the x. The first thing I'm going to note is that as x approaches 0, x and x both approach 0. So this is going to be one of those indeterminate powers of the type 0 to the 0. And because of that, we are going to rewrite this and see if we can follow through on our suggested approach. X to the x can be rewritten using properties of exponentials and natural logs as e to the x natural log x. And then let me remind you, the exponential function is continuous, which tells us we can take this limit and push it inside that continuous function. That is, we can write this as e to the limit as x approaches 0 from the right of x natural log of x. And this limit that results is one of our more familiar L'Hopital rule limits. And what I will typically do, just to kind of keep the work a bit more clean, is I will actually evaluate this to the side and then substitute in that value. So in this case, we have the limit as x approaches 0 from the right of x natural log x. As x goes to 0 from the right, x goes to 0, and the natural log approaches minus infinity. And as we've drawn the graph several times in recent videos, hopefully this is something that you can quickly and efficiently visualize. In fact, we've already evaluated this exact limit in one of our previous discussions. Let's just take it one step. I would write it as the natural log of x divided by 1 over x. Now as x approaches 0 from the right, ln of x goes to minus infinity, 1 over x goes to positive infinity, which means it's something that L'Hopital's rule applies to. I'm not going to go through all the details because we've previously done this, so I'll just say from a previous video, I believe part 2 in this series, the value of this limit ends up being 0. Now we can take this value of 0 that we got and substitute it back into the left. So remember what it is we're trying to evaluate. We end up with e to the 0, which is 1. So in this case, we've evaluated a limit of our first indeterminate power, and it worked out very nicely as we indicated using properties of exponentials and natural logs. At this point, what I would like you to do is use this work or idea that we have above as a template, pause your video and give yourself, I don't know, maybe 5 or 6 minutes and evaluate this remaining limit. So hopefully at this point you've paused the video and you've thought a bit about this example. Note, as x goes to infinity, if we think about the individual components, 3 over something big is going to 0. So the first observation we might make is individually this 3 over x is going to 0. Which that means is 1 plus 3 over x is going to 1, and x is going to infinity. So this is an indeterminate power of type 1 to the infinity. So the ideal scenario for us to apply our new technique. So rewrite this using properties of exponentials and natural logs. This would be e to the x natural log of 1 plus 3 over x. And because the exponential is a continuous function, we can plug or push the limit inside the exponential. But I do want to note that you actually need to physically show this step. Without this step, your work has a large logical gap in it. So it is necessary and required. Now we can go ahead and evaluate this all directly, or we could take the exponential out of the picture for a moment and just evaluate that limit. And I prefer to do that. It's less to write down in a sense. So if we think about the value of this limit, breaking the terms up individually, x is going to infinity, and because 1 plus 3 over x, recall, is going to 1, that means the natural log of 1 plus 3 over x is going to the natural log of 1, which is 0. So it's a 0 times infinity indeterminate form. I'm going to rewrite this algebraically. Instead of multiplying by x, I'm going to divide by 1 over x. I think that's the simplest way to rewrite this. Now the function in the top is still approaching 0. The function in the bottom is approaching 0. L'Hopital's rule tells us that this would be the limit as x approaches infinity, and we take the derivative in the top over the derivative in the bottom. In the top, we need the chain rule. Take the derivative of the outside function, evaluate it at the inside function, and multiply it by the derivative of the inside function. And note, algebraically, this simplifies rather nicely. We can note that the minus and the x squared cancel in both the top and the bottom. That leaves a 3 left over that's going to go to the numerator, and we have the single fraction 3 over 1 plus 3 over x. So this works out very quickly, very efficiently. Now if we think about what happens as x approaches infinity, well, the limit of a constant always approaches that constant. And as we noted a moment ago, 3 over x is 3 divided by something large, which must approach 0. You are more than welcome to break this up using limit laws, but as long as you've indicated what each term is approaching using arrows, as we've done above, it's perfectly reasonable at this point in the problem to write this as 3 over 1 plus 0, which is equal to 3. Now that we've evaluated the limit of the exponent that we had above, we can bring that back and see the value of our limit, e raised to the third power. And as usual, let me remind you that it's very important to use good mathematical notation. Your work for a problem like this should essentially look like what we have on the screen. Also, this is a great opportunity to practice problems. In fact, if we were meeting in person, we would now be midway through our second day of class discussing L'Hopital's rule. And I would write 3 limits down on the board, which you can find on the next page in the note sheet. And I would give you a solid 15-ish minutes to work in groups and discuss these problems. So I would suggest spending some time, at least 10, possibly 15, 20 minutes working through these problems before you view the next video. So stay tuned and take care.